Swayam Prabha. Digital India. Educated India.
Which were available and things like that. So, after learning all these things, naturally the next thing which comes is to start the analysis of two-phase flows, how to analyze two-phase flows. Now, before we go for the analysis of two-phase flows, what I would like to first cover is to cover a set of nomenclatures, some standard definitions and some standard some common terminologies. Those things I would like to cover, so that, because in this particular case what we find that in single phase flow situations we had one set of nomenclatures. Here we not only have twice the number, we have more than twice probably, because we have the nomenclatures, say for example mass flow rate. In this particular case it is the mass flow rate of phase 1, mass flow rate of phase 2, total mass flow rate. Under certain circumstances we also have the interfacial property. So, therefore, we find that the total number of properties are more than twice, and therefore, unless we define a definite set of nomenclatures, and it is not just the nomenclatures which we have used in our single phase flows, we have certain things more also, certain properties which were not certain parameters which were not necessary for single phase flows, those parameters will also come into being. So, therefore, what I decided was that before we go for any sort of analysis, it will be first prudent to cover up the set of notations or nomenclatures that we will be using throughout the class, so that as we proceed you will not have confusions regarding which nomenclature to use, how to use it, etc., etc. Now, if any of you want to choose or want to use some other nomenclature, some other notation, say for example, I will be using u for velocity. If you wish to use v, I do not have any problems, but in that case you have to specify that during your exams, etc. Why I would like to use u? Because I will be using specific volume for v for specific volume. So, therefore, just for and since we will be using so many properties, so many parameters, so therefore, I would like to first specify the list of notations and nomenclatures. We would first discuss the nomenclatures which are common both for multiphase and single phase and two phase flow situations, and then we will go for nomenclatures which will be used specifically for two phases or more than two phase flows, or in other words two phase and multi-phase flow situations. Okay. So, first we would like to specify all the nomenclatures which are there, and after that we would go for the different types of analysis which are usually practiced. We find that more or less the analysis types will be the same, but naturally they will be slightly more involved in this particular case. Now, since we are having two phases, so the first thing to specify is which phase is going to be 1 and which phase is going to be 2. Okay, that is the first thing, and after that we will be specifying the other things. Now, usually we find that suppose we are having two phases, say phase 1 and phase 2, then in that case normally we say that phase 1 is the continuous phase and phase 2 is the discontinuous phase. Well, how do we define the continuous phase and the discontinuous phase? I had already given you the definition earlier. A continuous phase is defined as one in which any 2 points can be joined by a line straight or curved, which passes through the same phase without crossing the interface. I would like to repeat it. A continuous phase is defined as one in which any 2 points can be joined by a line straight or curved, which passes through the same phase without crossing the interface. And a discontinuous phase is one which cannot be joined by 2 parts or 2 points of which cannot be joined by a straight or a curved line. Now, we can have circumstances when both phases are continuous. Okay. For example, in annular flow, if you remember, I we had a vapor phase or a gas phase and a liquid phase. If we have stratified flow, we find for these things both the phases are continuous. Now, when this is the situation, then in that case usually we take phase 2 as the lighter phase. So, therefore, this is usually the convention that for two phase flow, phase 2 it is going to be the discontinuous phase. When both phases are continuous, then in that case phase 2 is going to be the lighter phase. Now, you will find in several books for what usually people do, the conventions are, instead of 1, 2, under certain circumstances we would also like to denote it as LV, where L refers to the liquid phase and V refers to the, or rather sorry, it's we would prefer G, where G refers to the gas phase or the vapor phase. And we also have things like LG, where L refers to the liquid phase and your S refers to the solid phase. So, these conventions are also used under certain circumstances, particularly when we are concerned with phase transforms, maybe vaporization, condensation, etc. Under those circumstances, instead of 1, 2, we might go for LG subscripts as well. But for our case, usually I would like to prefer to use subscripts 1 and 2 according to the conventions which I have already mentioned. And also remember one more thing, when I use a subscript say LG, it refers to the difference between the gas and liquid properties. That means, this refers to the gas or the vapor property. You know most of the things, but then also I would like to repeat it just so that you are cautious while using it. It is just the difference between the gas property and the liquid property. For example, when we say HLG, it is nothing but it is Hg minus HL, and therefore, this is nothing but the latent heat of vaporization of this particular liquid. So, accordingly, if we use as HL, it is the heat or the enthalpy content of the liquid phase, Hg enthalpy of the vapor phase, HLG, it is the latent heat of vaporization or the difference between the vapor phase and the liquid phase, sorry, it is the difference between the vapor property and the liquid property when both under same temperature. This is the thing which you are supposed to remember. When both of them are at the same specified condition, usually it is the saturation, when both of them are under the saturated conditions. Now, if we take up say single phase flow, what do we find? We find that for single phase flow, what is the single most important parameter, can you tell me? For single phase flow, what is the single most important parameter which you measure whenever you have to quantify single phase flow? Volume flow rate or the mass flow rates, that is the most important parameter. So, normally for mass flow rates till now you have used m dot and things like that. For this particular class I would like to use mass flow rate, this is W. Okay. So, for single phase cases if you take up, this is going to be W. Accordingly, here what we have? We can have W1, the mass flow rate of the phase 1, which is usually for vapor liquid or gas liquid, it is the liquid phase. There will be W2, the mass flow rate of the vapor phase or the gas phase if it is a liquid vapor. If it is two liquids, then this is the mass flow rate of the heavier liquid, this is the mass flow rate of the lighter liquid. Agreed? Along with that, we also have W2 phase. You can also use Wm if you wish, but I would prefer to use W2 phase, which is nothing but equal to W1 plus W2. Agreed, from equation of continuity. Next, if we have the volume flow rate Q, okay. How do we define it? It is nothing but W by rho, isn't it? For two phase situations, what do we have? We are going to have a Q1, which is nothing but W1 by rho 1. We are going to have a Q2, nothing but W2 by rho 2, and we would also have a Q2 phase, which is nothing but Q1 plus Q2, is not it? Well, so after this, the next thing which we would have is certain things like, say, the density. Okay? We have already specified density while defining the volumetric flow rate. You can just write it down. This is the mass flow rate and this one was the volumetric flow rate. Next is if we have the density. In this case it is rho, here we have rho 1, we have rho 2 and we also have a mixture density rho Tp. How we will be defining it, that you already know and we will be discussing it later. Next we have a specific volume. I have a slide for this as well. So, I will be showing you the slide after I complete this, and VTP. And remember one thing which we have already discussed, that V1 equals to 1 by rho 1, V2 equals to 1 by rho 2, but VTP is not equal to 1 by rho Tp. Please remember this particular, this is something very, very important. We have already discussed it, I think, in the introduction class, is not it? After that, certain other properties, say for example, we have viscosity in this particular case. So, viscosity, you know, it is simply mu. In this particular case, we have mu 1, mu 2 and we have mu Tp. Okay? Now, we are considering two phases, they are flowing either concurrently or countercurrently, upflow, downflow, whatever it is, through any particular pipe. Okay? So, for that particular pipe, the cross sectional area of the pipe, it is going to be A. Now, for single phase flow, if you know A, it is sufficient. You can just measure the diameter of the pipe and diameter is, say, capital D. Please try to stick to these nomenclatures, because maybe the capital would be referring to one particular notation or one particular parameter, maybe the small letter will be referring to some other particular parameter, it can happen. Okay. So, therefore, for single phase flow, if you just measure the diameter of the pipe, the length of the pipe, you find out the cross section, it is sufficient. In this particular case, in addition to the total cross sectional area, it will be important for you to know how much of the cross sectional area is occupied by phase 1, how much of it is occupied by phase 2. So, accordingly, we have one A1 here, we have a A2 here, okay, where naturally A equals to A1 plus A2. Well, after that, after the cross sectional area, we have the wetted area, okay, the wetted area or the wetted perimeter, as you say. Okay. Usually, you can denote it as P, but I prefer to denote it as S. In this particular case, for two phase flow situations, we will have an S1. S1 denotes the area in which phase 1 is in contact with the wall. We would have S2, the area in which phase 2 is in contact with the wall. In addition, we are going to have an SI, the interfacial area as well. Okay. Certain other things are also important, which you did not use much for your single phase flows, but in this particular case we will be using them more or less quite frequently. One of them is the mass flux, the other is going to be the volume flux. Can you tell me how do we define mass flux? How do we define any flux for that matter? Per unit area. So, mass flux means mass flow rate per unit area, the total amount of mass which is flowing per unit time per unit area. Okay. So, therefore, mass flux we denote it by capital G, nothing but W by A. Okay. What is W? In terms of velocity, if you write, then this is going to be rho into U into A by A. So, therefore, G equals to rho U, is not it? This relationship is also quite important, we are going to use it quite frequently. In this particular case, what do we have? We are going to have a G 1 which is nothing but W 1 by A. Mind it, they are all per unit cross sectional area, not the per unit actual area which has been occupied. Okay. G 2, it is the W 2 by A, and finally, we have G T P which is G 1 plus G 2, is not it? Similarly, we have something known as the volume flux. We will not use it very frequently, but we will be using it. This is defined as small j, which is nothing but volume flux, means it is a volumetric flow rate per unit area, is not it? Accordingly, here we will be having Q 1 by A, J 2, it is Q 2 by A, okay, and then we will be having J which is equal to J 1 plus J 2. Agreed all of you? So, this we are going to have. Next we come to the velocity. How do you define velocity, you tell me? Velocity u, it is equal to displacement per unit time was in mechanical. In fluid, how do you define velocity? What is the velocity of flow? It is the volumetric flow rate, flow rate per unit. So, therefore, it is equal to Q by A. Agreed? For single phase, it is equal to Q by A. What about two phase? See, whatever I am teaching for two phase, the same thing is going to apply for three phase or other situations as well, only the number of properties will be more. Here it was J equals to J 1 plus J 2, they will be having J 1 plus J 2 plus J 3. Okay. Interfacial, instead of one interface, you will be having two interfaces, maybe J, sorry, very sorry, it is JTP, very true. Okay. So, therefore, here we have velocity equals to Q by A. In this particular case, what we can have? See, remember one thing, we are having two parameters Q 1, Q 2. We are having total cross sectional area A, and we are having A 1, the actual cross sectional area occupied by phase 1, is not it? So, if you talk about the actual velocity, then u 1, which is the velocity of phase 1, this should be Q 1 by A 1, is not it? The volumetric flow rate of phase 1 divided by the cross sectional area occupied by phase 1. Similarly, we can have u 2 Q 2 by A 2. Now, remember one thing, it is very difficult to measure this A 1, A 2. Okay. It is not very easy, because how much amount of, as I had discussed in the last class, how much amount of cross sectional area will be occupied by phase 1, how much of it will be occupied by phase 2, that depends upon the interfacial distribution, their density, their other physical properties, and so on and so forth. So, therefore, remember one thing, in single phase flow, velocity was a measurable parameter. We could measure, what we had to do, we had to just use any particular flow meter to find out the volumetric flow rate. We knew the cross sectional area of the pipe. So, therefore, velocity was an input parameter. We always used to refer that, see, water is flowing at 1 meter per second or 2 meters per second. In fact, Reynolds number is also defined on the basis of velocity, it is not on the basis of flow rate. But in this particular case, if we find that the velocity, it is no longer a measurable parameter at all, but we are very much used to mentioning the flow characteristic of any particular fluid in terms of its velocity. So, therefore, instead or apart from these local velocities which we say, these local velocities u1 and u2, the velocities which happen inside the pipe depending upon how much of the area has been occupied. Apart from this, we also have two other definitions of velocities. These are known as the in situ or the local velocities. Apart from this, we define something known as the superficial velocity, which again is a measurable parameter. So, that when we talk of the velocity, say air and water are flowing, we always mention as the superficial velocity of air is say 1 meter per second, the superficial velocity of water it is say 0.5 meters per second, where we define the superficial velocities as q1 by A, and this will be equal to q2 by A. So, therefore, you can very well observe, see, just by increasing one particular phase in the flow passage, what did we land up to? We landed up to 4 definitions of velocity in place of the single definition which we had for single phase flows. So, this will just give you an idea why I was so very particular about mentioning all the nomenclatures and things like that, even though most of the nomenclatures you have already used, because the number of parameters is increasing so many folds. So, unless we have a definite nomenclature, after some time when we go for the analysis, you will find you are completely lost in nomenclatures itself. If you are not very confident that this particular term will be referred, or rather will u refers to velocity, small v refers to your specific volume, capital V refers to the volume of bubble. If you are not very categorical about all these things, very frequently you will find that nomenclature itself becomes a problem in the analysis of multiphase flows. So, therefore, from this itself you can get an idea where we find that instead of a single velocity in single phase flows, we have come across 4 different velocities, definitions of velocities in two phase flows. We have 2 local velocities for the 2 phases, we have 2 superficial velocities. We define the superficial velocities as the velocity which the fluid would have had it flowed alone in the pipe. Okay. So, if only water, or say if only phase 1 would have flowed alone in the pipe, then the velocity which it would have was u1s. But now, with what velocity it has? It has the velocity of u1. Similarly, if only phase 2 would have flowed alone in the pipe, the velocity which it would have was u2s. Now, since fluid 1 is also flowing along with it, it cannot occupy the entire cross sectional area. So, what velocity it has? It now has the velocity u2. Okay. So, therefore, remember we have additional definitions of velocities in this particular case. Now, apart from this, see, whenever we have any particular flow of anything, say water, alcohol, whatever it is, first thing we would like to measure is its flow rate. Depending upon the flow meter available, we either measure, usually we measure the volumetric flow rate. There are mass flow meters by which we can measure the mass flow rate as well. And then while it is flowing through the pipe, this is the input to the pipe. Now, while it is flowing through the pipe, what we are interested? We are interested to find out the pressure drop. Depending on the pressure drop, we will decide which pump to use and things like that. So, the first hydrodynamic parameter which is very important is pressure drop. In this case also pressure drop should be the most important parameter. Okay. But we find usually pressure drop and pressure gradient, there are 2 things. Now, can you define or can you tell me what is the pressure drop? Usually as engineers we are interested in the pressure drop, and there is another thing which is known as the pressure gradient, which is the rate of pressure change with the axial distance. Okay. So, therefore, these are the two terms. We will be defining these two terms after we define a few more terms which are unique to two phase flow situations. Now, what are they? So, till now whatever terms I have defined, if you see in this particular slide it is available, whatever terms, please note this interfacial area, it should be capital SI, it is wrongly denoted here as small si, this should be capital SI in this particular case. So, these are the common terms which we have already finished defining till now. Okay. Now, apart from this, we find there are certain other important terms which have to be defined. For example, see, when it was single phase flow, what was the single most important parameter? It was the flow rate, mass flow rate or the volume flow rate. Along with mass or volume flow rate, we need to know the volumetric composition of the two phases which are flowing in the pipe. Just knowing their volume flow rates are not sufficient, because we know that moment we introduce them in the pipe, they do not flow in the volumetric flow rates in which they have been introduced. Why? Because they have got different properties, they have got different densities. So, the lighter phase tends to slip past the heavier one, as a result of which the in situ composition is different from the inlet composition. Okay. This I had already mentioned in the introduction part also. So, therefore, we need to have two particular parameters to define the composition. One of them is going to be the in situ composition, which is nothing, if we take it up as for gas liquid cases, then or vapor liquid or gas liquid or vapor liquid cases, it is nothing but the void fraction which we denote as alpha. Okay. And we all this is the void fraction. And there is one more thing which we defined, which is known as HL, which is known as the liquid hold up, where HL is nothing but it is 1 minus alpha, is not it? Okay. Very frequently we would prefer to, rather we would prefer to use liquid hold up instead of void fraction to specify the composition of the two phases. Why? Because suppose we have a liquid solid flow, we can use HL to specify the liquid hold up. If we have a liquid flow, we can use HL to specify the hold up or the composition or the fraction of the heavier liquid there. Okay. So, liquid hold up is a much more versatile situation, and we find that usually we have several cases where liquid is in a larger proportion as compared to the gas. Then under that circumstances, it is more accurate to measure the liquid fraction in the pipe as compared to the gas fraction. So, therefore, we find that liquid hold up is much more useful as compared to the void fraction. Although till now, wherever you have used any sort of gas liquid mixtures in absorption, in all sorts of mass contacting devices and such other applications, you were more acquainted with void fraction, but in two phase flow very frequently we would prefer to use the liquid hold up instead of the void fraction. So, it is usually the volume or the fraction of the total volume occupied by the heavier phase. Okay. So, therefore, usually what we do for this particular case is, so we specify it as HL. Okay. And we define HL as, now remember one thing, this HL or this alpha, it may not be constant throughout the entire channel. It may not even remain constant with time as well. There can be fluctuations with time, there can be fluctuations with your distance as well. Okay. So, usually we define HL as a, in this particular way, where this refers to the volume average liquid hold up. This is known as the volume average liquid hold up. We usually define it as the fraction of the volume which is occupied by the liquid phase, or in other words the volume occupied by the liquid phase divided by the total channel volume, V total. So, therefore, suppose we have a channel in this particular way, and suppose in here say suppose a gas and a liquid mixture is flowing. So, what we can do is suddenly at one instant, suppose we have a valve here, at one particular instance we simultaneously close both the valves. Then in that case what happens? Instantaneously the two phase mixture gets trapped here, and then once they are trapped, then they start separating by due to density, and then the heavier phase, if it is the liquid phase, it settles down here, the gas phase is at the top. If we have a graph paper or something here, we can easily measure the amount of the volume which is occupied by the liquid phase. We know the total volume of the conduit or the channel cross section which has been isolated. So, therefore, accordingly we can measure the liquid hold up in this particular case, or we can measure the gas hold up or the gas voidage as the case may be. Okay. So, therefore, this is the single most important parameter as far as your two phase flow is concerned, and we can measure it in this particular way, and we can relate it with the gas voidage in by using this particular equation. Now, remember one thing, when the flow is not uniform, it is not possible for us to measure either alpha or HL over a large length of the pipe, as I have shown in this particular case. Under that circumstances, what we do, you already know, we take a large number of infinitesimal measurements over say length dl, and then we can perform a time average at a given location, and under such circumstances your HL, when there are both temporal variations as well as variations with axial distance, it is usually given as HL as a function of r and t dr dt divided by, this is simply the normal averaging law which you already know. Okay. For circular pipes we can use in this particular way. Now, remember one thing that although we know that there usually we assume one dimensional flows. Okay. For most of our cases we assume one dimensional flow. What is this one dimensional assumption? That what is this one dimensional assumption, can you tell me? Exactly. It means that all the properties they vary in the direction of flow and there is no variation across the flow. Okay. Usually we assume that, but the assumption is not always correct. Under such circumstances we find out some sort of a correction factors in order to incorporate the three dimensional effects. And we also assume steady state conditions under several of the applications, which shows that the flow does not vary with time. But there can be circumstances when there are temporal variations as well as variations along the length. Under such circumstances we have to use some sort of averaging, and here this is the averaging which we do. Okay. Now, so remember one thing, that we have measured this your HL as the volume fraction of the total volume which is occupied by the liquid phase, or in other words we specify the in situ composition in terms of the volume fraction. Okay. And this is the actual definition. We would always like to define the in situ composition in terms of the volume fraction. But remember one thing, this has to be measured. This cannot be controlled by us, this cannot be an input, no flow meter directly will give you the measurement of the in situ composition, isn't it? So, therefore, it may not always be possible to measure the volume average composition. Why? Because as I have showed to you that to measure the volume average composition, what we have to do? We have to instantaneously stop the flowing mixture. So, in industrial applications, in practical situations, it will not be possible to stop the flow and to take measurements of the in situ composition. So, therefore, under such circumstances, we might have to measure the in situ composition across a particular area or maybe across a particular chord. Okay. Accordingly, we have different definitions of liquid holdup. For example, we have the volume average liquid holdup, we have the area average liquid holdup, we have the chordal average liquid holdup, and we also have something like the time average liquid holdup. Okay. But before we go to these definitions, I would also like to define certain other terms which we shall be using quite frequently. Now, since I have defined the in situ volume fraction, definitely there is something like the inlet volume fraction, and that is the input parameter which can be easily measured, isn't it? So, that inlet volume fraction, that is usually referred to as beta. This is the inlet volume fraction, which can be given as Q2 by Q1 plus Q2. So, therefore, remember one thing, alpha was defined in terms of the volume occupied. Remember, all sorts of volume, specific volume, every volume is defined by V. Therefore, please do not use V for velocity, which you have been doing so long. Okay, otherwise, we will be creating terrible confusions, and specific volume is small v, all other volumes are capital V. Please remember these things. Okay. So, therefore, remember one thing, the inlet volume fraction is defined in terms of the volumetric flow rate, whereas the in situ volume fraction, this is defined in terms of the volume occupied inside the actual cross section. And therefore, as I have already mentioned, alpha is not equal to beta, as a result of which, although beta this is a measurable quantity, this is a measurable quantity, but since we do not have any direct correlation between alpha and beta. So, therefore, alpha has to be determined, it cannot be controlled, it depends upon the physical, it is a function of the physical properties of the fluids, their density etc., and the physical properties as well as the phase distribution. This is the thing that you should remember. Apart from this, there is one more quantity also which I would very much like to mention. This is particularly applicable for boiling and condensation sort of things, that is the mass fraction of the total flow which comprises of the vapor phase or the liquid phase. So, initially it was the volume fraction which comprised, next it was the in situ volume fraction, next it was the inlet volume fraction. Usually under adiabatic conditions there is no mass transfer, and therefore, if you introduce W1 amount of phase 1, W2 amount of phase 2, then throughout the entire channel flow W1 and W2 does not change. Agreed? But when we are having some sort of heating arrangement, there is boiling, there is condensation, then naturally there is change of phase. Under that condition, W1 and W2 they are not constant. Okay? And under such circumstances, it is necessary for us to define the mass fraction which comprises of either the vapor phase or the liquid phase. From thermodynamics, we know that usually the mass fraction, it is defined as quality X, okay, where X is nothing but W2 by W, where you remember 2 is the lighter phase or the discontinuous phase, it usually refers to the vapor phase or the liquid phase in this particular condition, and 1 minus X is naturally W1 by W, or it is W1 by, we can write down in this particular way. Okay. So, therefore, we know that we can also write certain other equations and in the same way, just as I have told you for the void fraction, in this particular case also remember that there can be temporal variations, there can be variations across the flow. So, therefore, when we are talking about quality, usually we refer to the averaged values. Under normal circumstances, we do not put these brackets, and we assume that x refers to the average property itself, but when we have unsteady and or non-uniform flows, under such circumstances x has to be subjected to averaging properties. The average has to be taken over a specified surface for a particular period of time, and this is usually referred to as integral of the mass flux G2 dA dt divided by integral G dA dt. So, remember one thing, unless it is absolutely necessary, we do not put these brackets, but whenever we have unsteady or non-uniform flows, under that circumstances quality is also subject to averaging, and the average is taken over a specified surface for a specified period of time, and it is defined in this particular form. Now, remember one thing, just as we were discussing the flow patterns for a heated tube, we had inserted pure liquid at a temperature just below the saturated temperature, and as it was flowing up, it reached the saturated temperature, vapor started forming, and then we had bubbly flow and so on and so forth. Okay. So, remember one thing, this quality, this can be an input parameter, because this can be obtained if we know the amount of heat which is entering the pipe. Okay. That can be easily measured. Okay. If you know the heat flux, then it is very easy to find out the quality. Okay. So, therefore, unlike alpha or unlike the void fraction or the liquid hold up, quality is an input parameter. How to relate quality with the heat flux? Please note that heat flux, I am denoting it as phi. If you want, you can denote it as small q as well, but since already capital Q is volume flow rate, so therefore, usually I would prefer it to mention it as heat flux phi. Now, for heated tubes, in that particular case, we can always write down that phi into the circumferential area through which heat is applied. This much amount of heat, it goes into heating the liquid from its actual temperature to the saturated temperature, and then vaporizing that amount of liquid. From where sorry, it is not W into alpha, it is W2 into alpha, very sorry. And what is this W2? The amount of W which has vaporized, is not it? Or in other words, this can be written down as WCP T saturated minus T plus Wx into lambda, yes or no? So, from there we can find out x, this is nothing but equal to, do it and tell me, phi s minus WCP is not it? So, therefore, we find that we can measure the heat flux, the circumferential area or the perimeter, that is very well known. All these are simply properties, and therefore, x, it is a measurable parameter. Now, if we have liquid and vapor, any questions, any doubts, you are free to ask me. Any questions, any doubts, you are free to clarify it from me. Okay. So, this is the expression when we find that liquid at below saturation temperature is flowing. Okay. Now, suppose we have a liquid vapor mixture in equilibrium with one another. Under that circumstances, say if it is steam water flow, we can directly refer to the enthalpy values from the steam tables, and we can find out x, is not it? These things you already know, there is nothing to tell you. In that case, x is equal to H2 phase minus H1 by H2 minus H1. H1 is the enthalpy of the saturated liquid, H2 is the enthalpy of the saturated vapor under the same conditions as the saturated liquid. That means, H1, H2 both of them are measured at the saturated temperature T sat, okay? And this is the two phase enthalpy. So, remember one thing, we are using small h to denote enthalpy. For if you are doing heat transfer, then we will be using the small h probably to denote the heat transfer coefficient as well. But then according to the application you will be able to understand, we will not be doing much of that. So, I am not going to differentiate between the two, although there are textbooks who have differentiated. If in the later stage we require, then probably I will be going for some differentiation. For the time being, I am not using heat transfer coefficient. So, my small h refers to the enthalpy with the subscript denoting whose enthalpy it is measuring, whether it is the enthalpy of phase 1, it is the enthalpy of phase 2 or it is the 2 phase enthalpy. Okay. So, therefore, the thing is, whatever I wanted to emphasize is that although your void fraction was or your liquid hold up is not an input parameter, we cannot control it, your quality X is definitely an input parameter, we can control it. Okay. Now, if we can control it, if we know that X is a measurable parameter, we would naturally like to correlate X and alpha for heated tubes, is not it? We would also like to correlate the velocity and X. Okay. So, therefore, for heated tubes, for unheated tubes, how to measure velocity, how to measure void fraction, those things we can easily deal with. For example, let me tell you, as I have already mentioned that your X equals to, I have already said it is W2 by W1 plus W2, 1 minus X equals to W1 by W1 plus W2. Okay. So, therefore, I can write down W2, it is nothing but equal to your G into A, this is nothing but W into X, is not it? W1, it is nothing but G A into 1 minus X. Just tell me anywhere if you have any doubts. U2, what is the velocity? This is nothing but equal to W2 by rho 2 A2. U1, it is nothing but W1 by rho 1 A1. So, instead of this W2, we can substitute this W2 as W into X, yes or no? Same thing here, we can have W into 1 minus X, agreed? Can we do this? Instead of A2, what can we write? Can we not write it down as A into alpha? Yes, we can do it. Instead of A1, can we not write down A into 1 minus alpha? So, if we make these substitutions, what do we get? We get U2, this will be equal to Wx by rho 2A alpha, where this particular, what is this W by A term, can you tell me? This is nothing but G. So, therefore, this term can be written down as G. So, therefore, U2 equals to Gx by rho 2 alpha, is not it? So, this shows that X is an input parameter, G you already know if you know the total mass flow rate and the total cross sectional area, rho 2 is a measurable parameter. So, if you measure alpha, you can find out U2, if you measure U2, you can find out alpha. So, therefore, among the variables on which you have no control, you can find out a relationship. Same way for U1, you can write down this will be G into 1 minus X by rho 1 into 1 minus alpha. This can very well be written down, agreed? Okay. So, therefore, what were the parameters that we defined? First we defined the volume fraction, okay, or the in situ composition. Next we defined the inlet composition. After that the quality we defined, and two other very important parameters, they have to be defined. One of them, it is the relative velocity. Since all the problems arise due to the difference in velocity, so therefore, your relative velocity and the slip velocity, these two are very important. Or slip velocity, or in other words, this is usually known as the slip ratio. These two are very important. Okay. Slip ratio, usually it is denoted as K. This is equal to the ratio, or rather it is the ratio of the in situ velocity of phase 2 divided by the in situ velocity of phase 1. Usually we know that phase 2 is the lighter phase, phase 1 is the heavier phase. So, therefore, K is always greater than 1. Okay. And relative velocity, you already know, it is u2 by u1, and this is denoted as u21, isn't it? So, therefore, there is one very important thing which I would like to point out at this particular juncture. Just note, when you refer to relative velocity, it is u21 is u2 minus u1. You agree? If we define it as u12, this will be u1 minus u2. But in thermodynamics, if you remember, what does H12 refer to? H2 minus H1. When we say V12, it is V2 minus V1. So, remember one thing, the sign conventions in case of thermodynamics and in case of your multiphase flow is slightly different. Okay. So, therefore, the two other terms which I had wanted to define, one is the relative velocity, other is the slip ratio. These two are again very important. Okay. And we already know that u21 equals to minus u12. This also you know, and remember one thing, both alpha as well as the K, the slip ratio, they are functions of W1, W2, fluid property as well as conduit geometry. Okay. So, they are function of all these things. Okay. So, I would be ending up here. In the next class, what we will be doing is, we will be finding out a relationship between K and say the other measurable and non-measurable. See, K arises due to the difference in the in situ velocities. So, K should be a function of alpha. When we have phase transitions, then X should also come in. So, we will try to define a relationship between K and alpha, X, etc., based on whatever we have done today, and then we would also go to define a few other parameters which we could not define today. Okay. So, maybe we will be doing those things, and we will be continuing with our nomenclature chapter tomorrow as well. Thank you very much.